Bismillahirrahmanirrahim. Assalamu alaikum. Hello and welcome to lecture number 22 of Algebraic Topology. In today's lecture, we will continue of our discussion where we are trying to learn tools to calculate homology. So in particular, we will be interested in relative singular homology. And remember that we have already done this kind of things in simplicial homology when we calculated the simplicial homology of a pair. And then we will go on and see what is relative homotopy axiom. And once again, remember that we have seen the axiomatic definition of homology, and in that axiomatic definition, one of the axiom was relative homotopy axiom. Okay, so basically in this lecture we will see that singular homology satisfy that axiom. And then we will go on and see what is reduced homology, which will be useful in our next section, which will be part of our next lecture, and which is called Excision and applications. Let's continue with today's lecture. So relative singular homology may be thought of as generalization of the absolute singular homology groups. Okay, so of course we will see the reasons of this statement throughout this lecture. So in other words, we are trying to generalize the concept of singular homology with this new concept of relative singular homology. So as I said earlier, then that the whole discussion runs very parallel to the discussion of homology of simplicial pairs. Okay, so the same kind of calculations and the same kind of homological algebra machinery will be needed here in today's lecture. Let's review some definition from previous lectures. So starting from the definition of chain complex. So what is a chain complex? So a chain complex is an object like this. Okay, so in other words, it's doubly infinite. Okay, so it goes in this direction and in this direction, so it's doubly infinite sequence of modules. So basically these are modules. Okay, so in particular we will be interested in Z modules or free abelian groups. Okay, so in our case these CNs are Z modules or free abelian groups. Okay, so together with these homomorphisms, so between any two consecutive modules there is a homomorphism between them, and the most important property that these homomorphisms satisfy is that the composition of any two consecutive homomorphisms is 0. Okay, so that's the important condition. So in other words, we have a doubly infinite sequence of modules and homomorphisms between the consecutive ones such that the composition of any two consecutive homomorphisms is 0. So that's what is called a chain complex. Okay, so of course this condition has many implications. So partial I composition partial I plus 1 is equal to 0 implies, for example, that the image of partial I plus 1 is contained in the kernel partial I. Okay, so in other words, what we are trying to say that when I apply this partial q plus 1 on the elements of cq plus 1, then whatever the images are, when I will apply partial q again, then I will get 0 because the composition of any two consecutive maps is 0. So that's why whatever the image of partial q plus 1 is of elements of cq plus 1, so these images will be inside cq. So these are the images which belongs to the kernel of this partial q, because when we apply partial q on those elements we get 0. So that's why we can say that the image of partial q plus 1, or we can take this to be I, this is contained in the kernel of partial I. Okay, so of course there are many other consequences as well. So this is the definition of chain complex. Okay, now we know the definition of singular homology, and we have calculated singular homology. So in singular homology, so what we start from. Okay, so we have this space X, then we define these free abelian groups. Okay, so what is S and X? So basically this is free abelian group generated by all singular n simplexes. So what is a singular n simplex? It's basically a continuous function from the standard n simplex to X. Okay, so of course we know what is a standard n simplex. So if we consider all continuous functions from the standard n simplex to X, then the collection of those maps, those continuous maps, will generate this free abelian group SNX. Okay, or basically generate these group of n chains. Okay, and similarly we can define what is Sn minus 1. Of course this is the free abelian group generated by all continuous functions from n minus 1 standard simplex to X, and up to so on. And what is S naught X? This is the free abelian group generated by all continuous functions from 0 simplex to X. Okay, so in other words this is S naught X is the space is basically a free abelian group generated by all the points of X. Okay, so the basis of this free abelian group is a set of points of the space X. Okay, also we proved that the composition of any two boundary maps, okay, so these are called boundary maps, so the composition of any two consecutive boundary maps is 0. So in particular so this composition is 0. So in other words, if I calculate this partial n plus 1, compose it with partial n, then this is 0. Okay, and up to so on. So we have free abelian groups, and this is doubly infinite, so I can continue this side with 0 0 0 up to so on. So this is a doubly infinite sequence of modules, or in particular Z modules, or we can say free abelian groups. Okay, so doubly infinite sequence of free abelian groups satisfying this condition, and these boundary maps are homomorphisms. So we can say that this is basically a chain complex. Okay, so we have a chain complex, and in this chain complex we take S of minus 1 X to be equal to 0, and of course everything after this will be 0. So basically this is equal to S minus 1 of X. Okay, so the elements of Sn of X are called n chains, and the elements of Sn of X are of the form this. Now remember that there are many for example singular n chains. So this sigma is basically a singular n chain. So there are many, and so sometimes uncountable singular n chains. But what we take the elements of Sn of X are basically this combination. So these ni are integers, and these sigma i's are singular n chains, such that there are only finitely many ni are non-zero. Okay, so we can't take this sum to be infinite. Okay, so that's how we define Sn of X. Okay, and of course similarly we can do it for each and every free abelian group, and in particular if you concentrate on Sn of X, then we have seen that this is basically a free abelian group generated by all the points of X, and most of the time when you take for example a metric space or some other for example manifold, then this group is basically going to be uncountable, so generated by uncountable points, because it is a continuous. So for example if you take a manifold, then it is a continuous sheet of points, so the points are going to be most of the time uncountable. So but we take the elements of S naught of X to be of this form, so we always take this combination to be finite. Now similarly, if we have a subspace A of X, then A is a topological space on its own as well. So by considering A as a topological space, we can construct this chain complex. Okay, so it's the same procedure. We are following the same steps. Now the only difference between the topological space A and the topological space X is that A is contained in X, and otherwise it's the same construction. Okay, so now we have two chain complexes. So one chain complex is denoted by S lower star of X, and the other chain complex is denoted by S lower star of A. Okay. Now, as I've said earlier, that A is subspace of X, so basically there is an inclusion map from A to X. So we can say that I is a continuous, because it's an identity map. Okay, so the identity map restricted to A. Okay, so this is continuous function from A to X. And in the previous lecture, in the previous discussion, we saw that if we have a continuous function between two topological spaces, then this induces a map between the chains. Okay, so let's see how this is possible. So consider I have a chain in A, an n chain in A. Okay, so basically this sigma is an element of Sn of A. Okay, because this is a continuous function from the standard n simplex to A, so definitely an element of this Sn of A, which is the free abelian group of n chains. Now if we have this element, and since we also have this continuous function from A to X, so we can say that this sigma, which is a continuous function from delta n to A, we can compose these two functions, and we say that there is a map from this delta n to X. In other words, there is a continuous function. Okay, because sigma is continuous, I is continuous, so their composition is continuous, so we have a continuous map from delta n to X. So corresponding to every singular n simplex inside A, there is a singular n simplex inside X given by this. In other words, given sigma, I composition sigma gives me a singular n simplex inside X. So give me a singular n simplex in A, I will give you a singular n simplex in X. Okay, so now we can extend this I composition sigma by linearity. Now remember that I can do this composition only when I have only one singular n simplex, but if I have a combination of those, so for example if I have A1 sigma 1 plus A2 sigma 2, then how should I take composition with I? So we extend this by linearity. So when I say extend this by linearity, it means the following. So when I apply this I hash, so I hash is basically I composition sigma. So when you apply I hash, I sharp, okay, so sometimes people call it I sharp. So when you apply this I sharp on sigma, this is equal to I composition sigma. So we extend this by linearity means if you apply this on a combination, on an integer combination of singular n simplexes, then this is equal to A1 I sharp sigma 1 up to so on. Okay, so now I know how to calculate this I sharp sigma 1. So basically this is equal to I composition sigma 1, and similarly I know how to calculate this I sharp sigma 2. This is equal to I composition sigma 2 up to so on, and of course this is equal to I composition sigma n. Okay, so that's how we apply this I sharp to a general element of Sn of A, because the general element of Sn of A will be an integer combination of singular n simplices inside A, because it's a free abelian group generated by singular n simplices in the topological space A. Okay, so that's how we take any element of Sn of A and get an element of Sn of X. Okay, so get an n chain inside X. So this these elements So these are all elements which are singular n chains inside X, and when we apply them with some integer a1 a2 up to an and then add them together, then we get an element of Sn of X. In other words, this is an n chain in X. Okay, so we also proved the following thing. Okay, so we have a continuous function from a to X, and so we have this I sharp map from Sn of a, n chains of a to the n chains of X, and similarly I can define this I sharp map from n minus 1 chains of a to the n minus 1 chains of X. And we also have these boundary maps. So remember that there are two chain complexes, so one corresponding to X and the other corresponding to a. So for example, in this case n minus 2 a up to so on, and this is coming from Sn plus 1 a, and these are the boundary maps. Okay, so n minus 1, n minus 2 up to so on. So these are the two chain complexes, Sn plus 1 X, boundary n plus 1 up to so on, and we can continue on this side as well. Okay, so n minus 2, boundary n minus 1 up to so on. So these are two chain complexes, and this I, which is basically a continuous function from a to X, will give me these maps I sharp between any two maps like this. Okay, so between any two collection of n chains like this. So this map will go from the n chains of a to the n chains of X, and similarly I hash I star goes from n minus 2 chains of a to the n minus 2 chains of X. Okay, in fact this I sharp is a sequence of homomorphisms in. Okay, so sometimes if you want to be very specific about these n's, then sometimes we write it as in minus 1, in minus 2, and in plus 1 up to so on. Okay, so sometimes when you try to specify that this I sharp is between n chains of a to the n chains of X, then you write this I sharp as in. And similarly, when you want to show that this is basically a function from n minus 1 chains of a to the n minus 1 chains of X, so you can write I n minus 1 with subscript n minus 1. Okay, so also these I sharps or INs are basically homomorphisms. Okay, so this is all the discussion that we have already proved, and also this diagram is commutative, so I can follow this route or I can follow this route and I'll be reaching at the same point. Now consider the following exact sequence. Okay, so fix some q, and then consider this short exact sequence. Okay, now why this is short exact sequence? Because we know that we have an inclusion, so a inside X, we have an inclusion from a to X, and so this will be contained in inside SQ of X. So in other words, we can say that every Q chain in A can be embedded to SQ or Q chains of X. So every Q chain of A can be considered as a Q chain in X, because remember A is contained in X. So let's say this is X and let's say this is A. So when I take a continuous function from this standard and simplex to A, then basically I'm taking a continuous function from the standard and simplex to X, because A is contained in X. So that's why we can say that there is an embedding of SQ of A into SQ of X, so Q chains of A to the Q chains of X. Okay, so in other words, we are saying that there is an inclusion IQ from SQA to SQX, so the Q chains of A to the Q chains of X. Okay, so since this is an inclusion, so this is a one-to-one map, so we can write 0 on this side. Okay, now consider this part of the sequence. Okay, now if you take it to be Q chains of X quotient with q chains of A. Then basically this is an onto map, because this is a quotient module, and in this quotient module, what are the elements? So the elements of this quotient module are of the form x plus the q chains of A, such that x belongs to SQ of x. Okay, so that's why this is an onto map, because every element of this module. Okay, so once again we have seen that this quotient is a module, and so that's why this module is onto. So there is an onto map from SQ of x to this module, so we have a 0 on this side. Okay, so that's why we have this short exact sequence, and we denote this quotient module as SQXA. Okay, now the homomorphisms from SQX to SQ minus 1x maps the group SQL to SQ minus 1L. Okay, so once again, since A is contained in X, so these boundary maps partial Q takes singular Q simplices inside X and gives me boundaries of those singular Q simplices. Okay, so since we have A contained in X, so I can restrict this boundary map partial Q to the elements of A. Okay, so instead of L it should be A. So I can restrict this map to the elements of A, so that's why we have boundary maps, or we have homomorphism from SQA, so Q chains of A to the Q minus 1 chains of A. Okay, so we have this well defined homomorphism from Q chains of X comma A and Q minus 1 chains of X comma A. Okay, so why this is true? Because these boundary maps will take elements of SQX to the elements of SQ minus 1 fx, and will take elements of or Q chains of A to the Q minus 1 chains of A. Okay, so let's say we look at this definition of SQXA. So this is basically Q chains of X quotient with Q chains of A. Okay, similarly, what is this thing? So this is basically Q minus 1 chains of X quotient with Q minus 1 chains of A. Okay, so let's partition this thing. Now this SQX is contained in this thing, and these Q chains of A are contained in the Q minus 1 chains of A. Okay, so the upper part is contained in the upper part, and the lower part is contained in the lower part. So we can say that there is this well defined homomorphism. Of course we define this homomorphism using the boundary operator of this singular complex on X. Okay, so using these boundary operators we can restrict these to the Q chains of A and Q minus 1 chains of A, or in other words on the chain complex on A, and then we can use the same boundary operator to define this homomorphism between these two quotient modules. Okay, so because SQX goes to SQ minus 1x, SQA goes to SQ minus 1a, so that's why we have this well defined homomorphism. Okay, now since the homomorphisms are induced by the boundary homomorphism, so we have the following commutative diagram. Okay, so remember that this part is already commutative. Now we want to show that this part is also commutative. Now the point is when I have some element, let's call it sigma, in this structure, in other words, if sigma is a Q plus 1 chain in X, then when we apply UQ plus 1 on this element, then I get some element of this Q plus 1 chain in X comma A, and then we apply the boundary operator. Okay, now if I apply boundary operator first and then apply this UQ, then I reach at the same point, because in fact I'm applying the same boundary operator both times. So take this element to this quotient structure and then apply the boundary operator, or first apply the boundary operator and take this element to the quotient structure. It's the same thing, so that's why this is a commutative diagram. Okay, so this part we have already seen, but this is also true, because once again we are defining this part using this boundary operator. Now we can see that if I start from an element of sq plus 1 x, so in other words q plus 1 chain of x, so go this way and go this way and go this way, or I can start at the same point and go this way, go this way and go this way, or I can start from this point and go like this, like this and like this. So all these three routes are going to give me the same answer, and once again the reason is the same, because we are applying the same boundary operator. Okay, so if this is true, then we can say that the composition of any two consecutive boundary operators on this in this sequence, composition of any two consecutive boundary operator is 0. So that's why we can say that this is basically a chain complex. Okay, now let's see once again why this is a chain complex. So it's a doubly infinite sequence. Okay, so the first condition is satisfied. These are quotient modules, so remember that this is equal to q chains of x with q chains of a. So that's why we can say that it's a module again. Okay, so quotient module. Okay, so these are all modules. Next we have these boundary maps. So we define this using the boundary maps of the complex X. So using these boundary maps we can define these boundary maps, and the composition of any two is 0. Why this is 0? So once again using this reason. Okay, so I'm not going to elaborate this, because if you are confused, then we had the same discussion when we were discussing simplicial homology of a pair. So go back to that lecture and see the discussion. So let's recall another definition from our previous discussion, that what's a chain map. So we have two chain complexes, then a chain map between them, you can say that it's a sequence of homomorphisms. Okay, so we don't just need one map, we need sequence of homomorphisms. So c prime n plus 1 to c n plus 1, c prime n to c n, and c prime n minus 1 to c n minus 1. So we need these maps. Okay, so between these two we need fn plus 1, between these two we need fn, and between these two we need fn minus 1. Okay, so sometimes we call them collectively as f sharp. Okay, so what's chain map between two chain complexes? So it's a sequence of homomorphisms such that the diagram commutes. Okay, so in other words, if I start from this point and follow this route, or if I start from this point and follow this route, then I'm going to get the same answer. Okay, and this happens for each and every square contained in this diagram. Okay, so that's how we defined chain map. And if we can define a chain map or a map between two chain complexes, then of course we can also define what is exact sequence of chain complexes. So an exact sequence of chain complexes is basically a collection of maps. Okay, so from A star to B star we have P star, and from B star to C star we have Q star. Okay, so remember that this P star or P sharp, sometimes we denote it by P sharp. So remember that this is basically a sequence of homomorphisms. Okay, so in A star we have AN, we have an minus 1, we have an minus 2, up to so on, and in this case we have an plus 1, up to so on, and then we have on the other hand we have bn plus 1, we have bn, we have bn minus 1, we have bn minus 2, up to so on, and there are boundary operators as well. Okay, so partial n plus 1, partial n minus 1, n minus 2, partial n plus 1, partial n minus 1, partial n minus 2. Okay, so similarly we have cn plus 1, we have cn, we have cn minus 1, we have cn minus 2, up to so on. So there is this boundary operators in this chain complex as well. Okay, so these are three chain complexes. So one is denoted by A star, the second is denoted by B star, and the third is denoted by C star. So the short exact sequence of these three chain complexes is basically collection of these two maps. So basically P star is a collection of maps, these two collections, and Q star is a collection of homomorphisms. So these two collections of homomorphisms will give me a short exact sequence of these three chain complexes. So P star, so how we define P star? So we can write this map as P star, or I can write it as Pn plus 1. Okay, so this is P star, or in particular if we want to be specific, then it will be some map Pn. Okay, so collectively we are denoting this Pn with all of these Pni's with P star. So basically this is a collection where n belongs to integers. Okay, so similarly we have Pn minus 1, up to so on, we have Pn minus 2, and between B star and C star we have Q star, or in particular if we are taking a map from Bn plus 1 to Cn plus 1, this is Qn plus 1, this is Qn, this is Qn minus 1, this is Qn minus 2, up to so on. And then of course if P star is the map between A star and B star, then all these squares must satisfy the commutativity of the diagram. And similarly there is a map, Q star is a map between the chain complex B star and C star, so that's why this diagram should be commutative like this. Okay, and these are short exact sequences as well. Okay, so there is another condition that you start from 0 and end it at 0. So for example in this case you start from 0 and end at 0. Okay, so this part, this part is a short exact sequence. And similarly we have 0 and 0 on these sides, we have 0 and 0 on these sides, and we have 0 and 0 on these sides. So all these sequences are short exact sequences. So we have two chain maps, P star and Q star. So P star is the map between A star and B star, Q star is the map between B star and C star, and of course this commutativity of the diagram comes from the definition of P star and Q star. And we have these short exact sequences if we look vertically at the diagram. So that's what it means by short exact sequence of chain complexes. Now we can define this short exact sequence of S star A, S star X, and S star XA. So let me write it down quickly, that we have Sn A, we have Sn minus 1A, we have Sn minus 2A, up to so on, and this is coming from Sn plus 1 of A, up to so on. And then if we go lower, we have Sn minus 1x, Sn x, Sn minus 1x, Sn minus 2x, up to so on. Okay, so these are two chain complexes. So one is denoted by S lower star A, and the second is denoted by S lower star X. And then we can define Sn plus 1 xa, and this goes to Sn xa, and then this goes to Sn minus 1 xa, and then this goes to Sn minus 2 xa, okay, up to so on. And then we have these maps, okay. So what is this map? So this map is basically in plus 1, okay. And similarly we have this map in, we have this map in minus 1 up to so on. So in short I can just say I sharp, okay. And we can call these maps to be U sharp, okay. So in particular if we want to name, then we can say that this U sharp is a sequence of homomorphisms, and we can call this U sharp between the n chains of x to the n chains of xa to be a UN, okay. So there is a U sharp between these two chain complexes, so S lower star xa and S lower star x, and similarly there is this I sharp between S lower star a, so this chain complex, a singular chain complex of a, and then this singular chain complex of x, okay, and such that this diagram is commutative. And also we have, if we look at this diagram vertically, then there are zeros on these sides. So in other words we can say that this is short exact sequence of these simplicial complexes. So in other words we can say that we have short exact sequence of this singular chain complexes. Okay. Now let X be a topological space and A be a subspace of X, then the nth homology HNXA is defined to be this. Now remember that this sequence, okay, so this singular chain complex is basically a chain complex. So whenever we are given a chain complex, then we know from our discussion of homological algebra we can define these homologies, okay. So it's very simple, we have this chain complex, we can define these homologies, and we are calling this HNA. So that's how we define relative singular homology. Okay, so in our further discussion we will try to explore the properties of this relative singular homology, and we will try to see the relation between this relative singular homology and the singular homology that we are going to call absolute singular homology. Okay, so first notice that if we have a short exact sequence of chain complexes, then we have the following long exact sequence. Okay, so we have proved this and we are just using the result from our discussion of homological algebra. Given a short exact sequence of chain complexes, we have this long exact sequence. So we are just going to use this result. We don't need to prove it because we have already proved it when we were discussing the tools from homological algebra. And these maps, these delta n's, are called the connecting homomorphisms. So we have this short exact sequence, so we constructed this short exact sequence. So this is the singular chain complex on A, singular chain complex on X, and singular chain complex on the pair XA. Okay, now of course using that result of homological algebra we can say that we have the following long exact sequence, and these delta n's are basically the connecting homomorphisms, and this I star is coming from the inclusion of A into X. So I is the map from A to X, so that's why we call the map from S n, so n chains of A to the n chains of X to be I sharp, and then we call the map between their homologies. Okay, so nth homology of A to the nth homology of X to be I star. Okay, now the absolute singular homology is a special case of a relative singular homology. So why is this the case? So if we take A to be equal to phi, okay, then this SNA is trivial group, okay, because when the space is empty, then this SNA is going to be 0 all the way, okay. So basically we will get this picture, okay. And then on the other hand, we also know that from this picture, okay, so let's go back and see. So from this picture, so all the first row is basically 0. So what will happen with the rest of the row? So let's see. So we will have Sn plus 1x goes to Sn of x goes to Sn minus 1 of x up to so on, Sn minus 2 of x up to so on. So also this we have this Sn plus 1 x phi in this case, okay. So Sn of x phi, because we took A to be equal to phi, and so this is equal to Sn minus 1 x phi up to so on, Sn minus 2 x phi up to so on. Now also we have 0 on these sides, so basically these are short exact sequence when we look at this diagram, when we look at the columns of this diagram, okay. Of course this diagram continues on these sides, okay. So not 0, some Sn plus 2, and not 0, Sn plus 2 x. The diagram continues on this side, okay. So these are the boundary maps. Now if this is a short exact sequence and we have 0 0 and Sn minus 2x, Sn minus 2x phi, so let's consider this thing, okay. So 0 goes to Sn minus 2, x goes to Sn minus 2 x phi, okay, and this goes to 0. So this is a short exact sequence, so the image of this must be equal to the kernel of this. So the image of this is 0, so the kernel of this must be equal to 0. So in other words, this is 1 to 1, and similarly the image of this must be equal to kernel of this. Now the kernel of this map is basically the whole space, and so the image of this must be the whole space. So in other words, this is onto as well. So we have a 1 to 1 and onto homomorphism between two spaces, so in other words they are isomorphic. So this is basically an isomorphism, and up to so on, using the same argument, we have all of these things are isomorphic. So in other words, when we define the homology of this chain complex, so S lower star of x, then this will be isomorphic to the homology of this chain complex, okay. So that's why we can say that these nth homology of this topological pair xa, this is equal to the nth homology of x if we take A to be equal to phi. So in other words, we can say that by taking A to be equal to phi, this relative homology becomes this absolute singular homology, okay. So let's consider an example. If x is a one-point space, then this relative homology is 0. So why this is the case? So if A is empty, okay, so there are two options. Either A can be empty, because A has to be a subset or subspace of x, and x is one point space, so there are only two options for A. So A could be empty or A could be one point, okay. So in both cases, okay, so these are 0. So let's see how, okay. So let's sketch two diagrams, one corresponding to the case when A is empty and the other corresponding to the case when A is a point, okay. So let's sketch this diagram when A is empty. So if A is empty, then the complex corresponding to A will be 0 all the way, and this Snx up to so on, Sn minus 1x up to so on. So we have this singular chain complex corresponding to X, and then we have SNX A, this relative singular complex. Okay, so once again we have 0 on these sides. Okay, so this forms a short exact sequence. So if we look at the columns, then there will be zeros at the top and bottom. So in other words, we can say that this is a short exact sequence. So if this is 0, since A is 5, so this chain complex will be zeros all the way. And so this Sn of X is isomorphic to Sn X. So the relative homology is isomorphic to the absolute homology, and we know that for point, okay, so for point Hn of X is equal to 0 whenever n is greater than 0, and since this is isomorphic to the relative homology, then this is also equal to 0 whenever n is greater than 0. Okay, now let's consider the case of n is equal to 0. Okay, so once again, when a is equal to phi, then in the case of n is equal to 0, we know that this okay, so we know that S naught of X is isomorphic to S naught of X A, because A is equal to phi. Okay, so when we continue on this chain complex, that at the end there are zeros in this row, so that's why we can say that for 0 as well. So for the case when A is equal to phi, and so these things are isomorphic. So why? Because we know that H naught of X is Z, and since these are isomorphic, so we can say that this is equal to the relative homology of X with respect to A when A is equal to phi. Now let's consider the case when A is equal to 1 point and equal to X, since X is a 1 point space, so A is equal to X. So in this case, now let's see what will happen. So S naught S1 of A, S naught of A to 0, S naught of X goes to 0, S naught of XA goes to 0. Now we know that when we calculated the homology of a point, then we know that H naught of X is isomorphic to Z. But now let's see what will happen in this case. Since A is 1 point, so this is isomorphic to Z. Okay, so this is basically S naught A, and X is a point, so this is also isomorphic to Z. So this is basically S naught of X, and this goes to let's see what will be the quotient. Okay, so this S naught XA is basically quotient of S naught X with S naught A. So that's why we can say that this is 0, because both of them are Z, so the quotient is going to be 0. So then we can say that H naught of XA is 0. So the relative homology of a point when this subspace A is equal to X is going to be 0. So that's the difference between relative homology and the absolute homology. Now let's consider another example. Okay, so if X is disjoint union of path connected components, okay, so let's say X is something like this, and A is some subspace of X, let's say A is something like this, then we have the following result. So the proof is not included, but it's very simple and it runs very parallel to the case that we did for absolute homology. Okay, so we also did the proof for simplicial homology as well, so just follow the same steps and you will get the proof. And if X is path connected, then this is equal to 0. So why this is the case? So just use this diagram once again, SNA up to so on. Okay, so SNX and SNXA. So use this diagram and you will get this result. Okay, so just like the example that we did for the one point space, we can also prove this result. Now if we have a continuous map of pairs, so when we say that we have a continuous map between two pairs of topological spaces, it means that f is a continuous function from x to y and f of a is contained in b. Okay, so now if we have this continuous map of pairs, then we have this thing, because we have a continuous function from x to y, then we must have this map between these two chain complexes. Okay, and also f is a map from a to b and it is also continuous. So when we restrict this f to this subspace a of x, then we have a continuous map from a to b. So of course this will always also give me this chain map between the chain complex of a and the chain complex of b. Okay, also we have this fact. Now this is a simple fact, so when we will sketch the chain complexes, and then you will realize that this is true. So f sharp induces a chain morphism. Okay, and now once again we have many chain complexes in this situation. So unfortunately I can't sketch it over here, but it's a relatively trivial exercise to see that we have the following chain morphism. Okay, so remember that corresponding to x and a we have one diagram. So corresponding to x and a we have the following diagram: Sn a, Sn minus 1, a up to so on, and Sn x, Sn minus 1x up to so on, Sn x a, Sn minus 1 x a up to so on. So we have this maps, and there are zeros on the other sides. So so this is a short exact sequence of three complexes. And similarly, corresponding to y and b we have the following diagram: Snb to Sn minus 1 b up to so on, and Sn y, Sn minus 1 y up to so on, and similarly Sn yb up to so on, Sn minus 1 yb. Okay, so we have these two short exact sequences between chain complexes. Okay, so we have this short exact sequence of chain complexes and this short exact sequence of chain complexes, and so this result says that when you have this SNXA, and there is an induced map from this to SNYB. Okay, so why this is the case? Because we have a map from this chain complex to this chain complex as well. So we have a map from this chain complex to this chain complex, so this is called F sharp, and we have a map from this chain complex to this chain complex, this is called F sharp. Okay, so it says that this map is also well defined, which takes this chain complex to this chain complex. Okay, so if we have this map, then it will give me a homomorphism from the nth relative homology to the nth relative homology of YB. Okay, or simply we can write it down as F star from H star XA to H star YB. So this star means that it's true for each and every value of n, so when we replace this star with some n, then this is true. Okay, so that's how we get given a continuous function between two topological pairs, we have a homomorphism between the relative homologies of those pairs. Now we also know that the category of topological pairs, or pairs of topological spaces, is denoted by top 2. Okay, so the objects are basically topological pairs, and the morphisms are just we discussed, that a continuous function from x to y such that f of a is contained in b, and all other properties are also satisfied. So we have this functor, okay, so Hn, which will take a topological pair and give me groups. Okay, so it will give me xa, and if there is a continuous function between xa and yb, then it will give me this function, which I can consider as the image of f under this n for fixed n. Okay, so we have a basically functor from the category of topological pairs to the category of abelian groups. Okay, so basically we are not going into much detail of these things. So if you have any questions, then you may have a look at the book of Joseph Rotman or Alan Hatcher. Now we have another result from homological algebra. So this result says that if you have this diagram, okay, so let's see, so the first row of this diagram is a short exact sequence, the second row is another short exact sequence, and we have the following maps f prime, f and f double prime between them, such that the diagram is commutative. Now if we have this short exact sequence, then we have this long exact sequence. Okay, so we have proved this result, and we have, if we have this a short exact sequence, then we have this long exact sequence. Okay, and this result says that if there are f prime, f and f double prime such that the diagram is commutative, then we have these maps f prime hash, f prime, f double prime hash, such that the diagram is commutative. Okay, so once again we are not doing the proof of this thing, and if you are interested, then you may have a look at one of the reference books. So for example, Joseph Rotman and Alan Hatcher. So if we have two continuous maps between these two topological pairs, and if these two functions are homotopic, okay, so relatively homotopic, so relative to this space A, then what is the relationship between f lower star and g lower star? Okay, so now remember and compare this discussion with the discussion that we did for absolute singular homology. Okay, so there we proved that if two functions are homotopic, then their images under this functor Hn are equal functions. Okay, so in this case it is also true, but before that let's have a look at the definition of relative homology. So it's a recall. So if A is a subspace of X and we have two functions f0 and f1 from x to y, and these are continuous functions, then we say that f0 is relative homotopic to f1 if the following conditions are satisfied. And of course f0 restricted to A is equal to f1 restricted to A. Okay, so f0 is relatively homotopic to f1 if there exists a continuous function capital F such that it is homotopy of f0 and f1. In other words, when I take t to be equal to 0, then it will give me f0, and when I take t to be equal to 1, then it will give me f1, and this is a continuous function. But if we want these two functions to be relative homotopic, then we impose this extra condition that for each and every t, these values, okay, so vary this small a from the capital A, and for each and every a, these functions are equal. Okay, so for each and every t this happens. So in other words, let's say we have this f0 and we have this f1, and they are equal on some subspace A. Okay, so let's call this to be A. So they are equal on this subspace A. Okay, so this is f1. Now it says that f is basically relative homotopy of f0 and f1 on this subspace A if for each and every t. Okay, so you start from f0 when t is equal to 0 and you end it at f1 when t is equal to 1, and for each and every intermediate t the values at A are equal. Okay, so it's basically something like this. Okay, so the values are equal. Okay, so that's some sort of a relative homotopy. And of course if instead of fixing this A, if you fix the endpoints, if you take this A to be endpoints, then the situation will be like this, and this is basically homotopy of loops. So instead of taking this A to be like this, if you take A to be the endpoints, then it will be something like this. Okay, so that's what it meant by relative homotopy. So now we have this relative homotopy axiom. If we have continuous function between two topological pairs and they are homotopic, relative homotopic with respect to the space A. Okay, so when we are saying relative homotopic, it means with respect to the space A, then their images under the functor Hn are equal. Okay, so this star means that this is true for each and every n. So in particular Hn of f is equal to Hn of g for all n. Okay, so the proof of this is not included, but once again if you are interested, then you may have a look at the book of Joseph Rotman or Alan Hatcher. Now remember that we have already seen the axiomatic definition of homology, and one of the axiom number 5 was homotopy axiom. Okay, so it says that if we have two continuous functions between these two topological pairs and which are homotopic, then f star is equal to g star. Okay, so basically we have proved some axioms for the singular homology of this definition, and we have shown that singular homology satisfies these axioms. Of course we have shown only few axioms. Now let's begin with the last section of today's lecture, reduced homology. So we have defined what is relative homology. Now the following question arises: is it true that this relative homology is equal to the homology of the quotient topology x with taking quotient x with A? So in general this is not true, but to answer this question and to find the relation between the relative homology and the homology of the quotient topology, we are going to define reduced homology. So in this reduced homology, instead of considering this chain complex, so we add one extra map and one extra node to this chain complex. So what is this map? So map is called epsilon, and this extra node is just z. And how we define this epsilon? So remember that S0 x is basically a free abelian group generated by the points of x, and so the elements of this are of the form ni sigma I, and so when we apply epsilon on this ni sigma I, then this is equal to just sum of these coefficients, and of course this is going to be an integer because S0 x is a z module. Okay, so this is z module, so these coefficients ni are basically integers, so ni are integers. So that's why we can say that when we define epsilon like this, then this is going to be an integer. Okay, so when you consider this chain complex, then the homology defined by this chain complex is called the reduced homology of x. Now let's see the relation between homology and reduced homology. Now observe that in case of reduced homology we have this longer chain complex, and in case of normal homology or chain complex ends with 0, and this is the boundary map partial 0, this is the boundary map partial 1, and S1 of x. So rest of the homology groups are going to be the same, and the only difference is going to be at when n is equal to 0. Now let's see what will happen at 0. Now this h naught tilde of x is basically equal to, okay, so the kernel of epsilon quotient with image of partial 1, and this h naught of x is equal to kernel of partial naught. Now the kernel of partial naught is the whole s naught, so we can say that the s naught of x quotient with the image of partial 1. Now also the composition, so since this is a chain complex, so when we apply partial 1 and then we apply epsilon, then we are going to get 0. So in other words, when I apply epsilon on the elements of image of partial 1, then I'm going to get 0. Okay, and I can apply this epsilon on the elements of s naught of x and I will get integers. So there is a well-defined map given by epsilon, so let's call it epsilon prime, which starts from h naught of x and goes to z. Okay, and this is so this is the map defined from epsilon. And similarly the kernel of epsilon is contained is s naught of x, so there is this inclusion. Okay, so if this is an inclusion, so we have this 0 over here, so this is inclusion, so 1-to-1 map, and we have this z over here, and so we have this short exact sequence. Okay, so if this is the short exact sequence, then we can easily say that what's the relationship between this and this. So this center homology is going to be equal to h naught of x is equal to h naught of x tilde direct sum with z. So that's the relationship between homology and the reduced homology. Okay. And in particular, if I have this space to be just one point space, then I can follow the same procedure and then I can calculate this thing. So let's have a look. So this homology must be equal to reduced homology direct sum with z. Okay, so in other words, this must be equal to the reduced homology direct sum with z. And we also know that h naught of x, if x is a point, then this is equal to z, and the rest of the homology groups are 0 for the point. And since they are equal, so we can say that h naught of x tilde, so the reduced homology of the point is 0. So we can say that h tilde n of x is 0 for all n. Okay, so we don't need this bracket, so this is 0 for all n for reduced homology, and this is not the case for singular homology, because we calculated that this is equal to 0 when n is greater than 0, and this is equal to z when n is equal to 0. But this is not the case for the reduced homology. So this is one of the important consequences of the definition of the reduced homology, that when we calculate the reduced homology of a point, then all the homology groups are 0. Okay, so these are the relations. Okay, so remember that when we were trying to define reduced homology, then we said that we are going to find a relation between the relative homology and the quotient space homology. So that's the relation. So if you want to calculate the relative homology of a pair of topological spaces, then it is the same as calculating the reduced homology of the quotient topology. Okay, so that's an important thing, and these kind of results are going to help us. Okay, so to help us in understanding the homology, to help us in calculating the homology in difficult situations. Okay, also the reduced homology is basically equal to this relative homology. Okay, now if you look at these two results, then you will realize that these two results are going to be very important in calculating the homology. So obviously we are going to use these results in our further discussions in next lectures, and we will see how these results are important in calculating the singular homology. So next time we will see what is excision with applications. Okay, so with applications means we will be trying to apply all of these results to calculate the homology. This is the end of the lecture. Thank you very much, and Allah Hafiz.